All right, so what we're going to be talking about is delta H. Delta H is enthalpy, which is a very fancy name for heat.
Heat.
Okay? And we've talked about heat of reaction off and on all year. Okay? Delta H is one of three thermodynamic quantities. There's a delta H, a delta S, and a delta G. Delta S is entropy or disorder, and delta G is Gibbs free energy or spontaneity. Okay, but we're going to focus on the heat. Now, the first thing is delta H is a state function. How many people read that over the weekend? It's on the very first page. Okay?
Yeah.
Did anybody figure out why we care, what that meant?
No.
Like the spontaneous something.
Combustion.
Okay,
What?
well, there's spontaneity and delta G. Most people can't figure out why the heck we care it's a state function. Okay? Yes, the state function depends on states, but here's the big thing. This is what I want you to focus on. A state function depends on where you start, so maybe initial, and where you end, final. Okay? Now, here's the cool thing about that. I know that sounds like a really simple statement, but what it means is this. If we were to calculate the change in heat from initial to final, we could do it directly in one step. This would be the delta H of, let's call it a process, because this could be for a chemical reaction like combustion or neutralization, but it also could be the delta H for the melting of ice or the boiling of water. We've done that. Remember when we did this? Heat up the solid, melt it, heat up the liquid, vaporize it, right? Okay, we were doing delta H's in here. So it can be a chemical or a physical process. But here's the cool thing. We could also start from our initial position and go to another position. Let's call this delta H1. Then we could go to delta H2. We could go up to delta H3. Then over to delta H4. And then maybe down to delta HF. Okay? In the end, the delta H of your process will be the same, no matter if you go there directly or if you go an indirect route. Okay? I guess the best analogy that I can think of is like balancing a checkbook. Okay? If you make $200 and you spend $200, you got a balance of zero.
You save zero.
Okay? Yeah.
I just leave it on that.
If you make $200, you spend 10, then you spend 20, then you have a babysitting gig, you make 35, and then you could do a bunch of little transactions in and out, but if you end up in the end spending as much as you started with, you have a balance of zero, right? So that's kind of like a state function. Something that would not be a state function would be distance. The distance between this point and this point is a lot shorter than the roundabout way. So distance would not be a state function. What did you say? The what?
Displacement.
Yeah, displacement. Okay, Michaela?
So delta H1 through delta H4 is equal to delta HI.
To F.
Okay.
Yes, exactly. Okay, why do we care? All right? The cool thing about it being a state function is it means there's several ways we can solve for heat. Okay? We're going to learn 4 of those ways. Okay? We don't always have to be super direct. And that's basically what a state function helps us do. Okay? All right. The first way we're going to learn is calorimetry. Okay? How many of you remember that silly video, calorimetry, yo, and they would do MC,
Delta T.
Okay? I'll try and put that video up on E-Class for those of you who never got that, that great experience, or those of you who just crave to have it again. Okay? But how many of you do remember MC delta T? Okay? Some people call it MCAT, right? Heat equals MC delta T. Now, we are going to use this to figure out a process, okay? The reaction we're going to work on today is going to be the combustion of ethanol. C2H5 OH, and we're actually going to choose the liquid form. Now, when we combust something, what do we add?
Oxygen. Because
Yeah.
that forms CO2, right?
And then the product, one of the products is CO2. What's the other product? Water. Exactly. Now, it's going to be very important for us to specify our states of matter. What's the state of matter of oxygen at room temperature?
Gas.
Gas. Okay? Now, what do you know about combustion reactions? Are they endo or exothermic? They are exo. We kind of know that. Not all reactions will you know that. You'll kind of have to use your calculations to figure it out. But CO2, won't that be in the gas state? And then if we're burning things and creating heat, what's the most likely state of matter for water?
Gas.
Gas. Okay? All right. So, and then let's balance. We have 2 carbons here. We've got 5 and 1, 6 hydrogens, so we need a 3 here. That's 4 plus 3 is 7 oxygens, but we already have 1. So what does this need to be?
3.
A 3. Okay. So here's our balanced reaction. Now, what we're going to do is we're going to take 1 gram of this. Okay. We're going to take 1 gram and we are going to burn it. How many of you guys remembered in Chem 1 where you burned a marshmallow?
Yeah.
Okay.
Will we make it smaller?
And we burned a marshmallow underneath some water that was suspended in a little soda can.
Oh yeah, and then yeah.
Okay? Now,
Hold on, I
we
think I have a
tend not
picture.
to use a beaker because glass itself takes a little while to heat up, meaning it absorbs a lot of heat itself. But metal absorbs very quickly, okay? And it transfers the heat very quickly. Even though there's going to be a little bit of lab error, we're going to put the water in an aluminum can, and we're just going to kind of pretend that all the heat from our burning alcohol, so there's a little dish of alcohol and there's the red flame, that all the heat from the burning alcohol is going to be absorbed by the water in the can. We know there'll be a little bit of lab error. Okay, but let's go with this. All right, so let's collect some data. First of all, we're going to measure a very specific amount of water, 100 mils. We're going to measure our initial temperature of water, 20. And we're going to measure our initial grams of C2H5OH. Okay? We're going to light it on fire. Burn, baby, burn. Okay? And we're going to let the temperature rise until it stops rising. Okay? We're going to let all the alcohol burn. Okay? And what we find is the final temperature is 84 degrees Celsius. Okay? So now we're ready to use our formula. MC delta T. But here's my question before you start. Am I going to use the mass, the specific heat, and the delta T of my alcohol or of my water?
Water.
Okay, why of the water? You're right.
Yeah, it's the one.
Because the water is
What's changing?
what's yeah.
Okay? Well, this is changing, but what is it changing into?
Into that.
Okay? This doesn't have, it has a specific heat if all we were doing was heating it up, right?
Yeah.
But what we're doing is we're actually chemically reacting this. That specific heat isn't going to stay the same, right? So it's not going to stay the same at all. So actually what we're doing is we're indirectly measuring the heat of this reaction by calculating the heat the water absorbs from the reaction. So yes, we are going to use the mass of the water, the specific heat of the water, and the change in temperature of the water. Okay? What is the mass of the water?
That was 18.
Nope. That's molar mass. But what's the mass that we actually have in the can? We have 100 milliliters. What's that in mass?
100.9 grams.
It's 100 grams.
It's 100 grams.
Okay? Water has a density of 1 gram per milliliter. Okay? You can assume that unless it's stated otherwise. Okay? Who knows the specific heat of water?
It's
3.1.
4.18. Very good. It's 4.18 joules per gram degree Celsius. Was anybody going to guess 1? because the other specific heat in calories
Yeah.
per gram degree Celsius is 1. But because all of these heats that we're going to be using are in joules or kilojoules, I wanted to use this one. This is not a number you have to memorize. Okay? All right. What's the delta T? You're right. 64. Okay.